Welcome to the lectures on high voltage engineering. In today's lecture, we are going to study or discuss the voltage Doubler circuit, also known as Cockcroft-Walton multiplier circuit. In today's video lecture, we are going to discuss the practical aspects of voltage Doubler circuit, and we will also study how to design the practical circuit of Cockcroft-Walton multiplier circuit. If you are not familiar with the basic working of the Cockcroft-Walton multiplier circuit, you may refer to my previous video lecture, which is already uploaded, that how this voltage multiplier works. Here in this lecture, we will be covering some practical aspects which are very useful and very important when you are going to build a Cockcroft-Walton circuit for your lab, for your project. And so this lecture is very important from practical point of view. So let's start with some basic revision of the circuit of the Cockcroft-Walton multiplier circuit. Here as a review, it is represented the basic circuit of the Cockcroft-Walton multiplier circuit. Here you can see that as I told you in the previous lecture, that we have these stages of this Cockcroft-Walton multiplier circuit. This is the first stage where you achieve the doubled voltage, and here we have the AC power source, AC power at the input. Here you have the capacitor C1, the diode D1, the capacitor C2 and the diode D2. So this is the first stage, and you can see that in the first stage we have two diodes and two capacitors, and then we can have n number of stages. So how many capacitors we can have here? First stage has two capacitors, then two stages will be having four capacitors. So these numbering, if you can observe here, this is D1, this is D2. In the similar way, if this is C2, then this is C4 and this is Cn. So this diode will also be represented by D2n, and this diode will be represented by D2n minus 1, and this capacitor is C2n minus 1, because you can see that here we have two diodes and two capacitors in one stage. So in nth stage we will be having twice number of diodes, like D2n. So as we named it as like D4 and D3, so we have, in the similar fashion, we have given them the standard rotations. So this is your nth stage, and where we connect the output or load voltage, here we connect the load. This is load resistance. Now what is the load here? Loads are actually here we have like the test object, like it can be like two electrodes in the air, or it can be a test object which has to be tested on the high voltage. So what is the V out? So here now there comes the difference between the theoretical approach and the practical approach. In most of the textbooks and in most of the theoretical literature, you will be observing, like you have studied in a previous lecture, that output voltage from the Cockcroft-Walton multiplier circuit is equal to 2NV max. Like it is actually doubling up the voltage, but this is what the theoretical value. And interestingly, you cannot achieve this voltage practically, because this is the value when your Cockcroft-Walton circuit has no load, has no any test object. Under that condition, it is able to develop the voltage, but when you connect the test object, then the output voltage is not the twice. Like here you have, now what is V max, by the way? V max is the peak voltage of the AC power source. V max is the peak voltage. Obviously AC power source is sinusoidal in nature, so V max will be its peak value. And if you have only the single stage, then the voltage will be twice of this voltage across this capacitor. So this is what the this is what the theoretical value, and our task here is to design this Cockcroft-Walton multiplier circuit. We have to study something that we are able to practically design this Walton circuit. So moreover, let me revise you from the previous lecture video. What we discussed, that we started studying its working from the input starting from the negative half cycle. That we claim that our input voltage is like that, it starts from the negative peak. We can also study using by assuming that input started from the positive half cycle, but then again its working actually starts with the negative half cycle. So what we said, that it starts from the negative half cycle. Now what happens here, you have the diodes. You can see here, first what will happen when there is a negative half cycle, the diode D1 conducts and the capacitor C1 charges to the maximum value of this input voltage, which is V max. And upon the next positive half cycle, what happens, the voltage here and this voltage, they add up and the diode D2 conducts and the capacitor C2 gets the twice charge as that of the input voltage. Now this is what the truly the theoretical concept, and practically this value appears, but whenever, as soon as you connect the test object, or even you connect an object for measuring the high voltage, it draws current even in the microamperes or milliamperes. What happens as a result? The voltage drops. So the practical voltage is not that the twice of that voltage. More to add, I would like to add that these diodes, which are odd number diode like D1, D3, D2 and -1, these diodes conduct during the negative half cycle, and the diodes like D2, D4 and D2n, the diodes with the even numbers, they conduct during the positive half cycle. Another most important concept here is that you can see that here you have an AC power source and here you have diodes. So whenever you have diodes and the AC power source, it means that here is the phenomena of rectification. And now what is meant by rectification? That is, you are converting AC into the DC. So as you are well aware that the output of the rectifier is a kind of a DC value. Obviously if it is a DC, like either it is in the form of this kind of DC which we obtained from the rectifier. So we have always a mean value here, the mean value which is the DC value. So we are interested in this DC value, and these are the voltage ripples. So practically you will be observing these voltage ripples, and there is a mean DC value. And what are the ripples, and what is this DC? What will be that DC value? And what are the effects of the loading current IL? What are those effects, and what is the significance of the value of the capacitor? What value of diodes we should be choosing? These are the practical concerns. Okay, so got my point that here you will be having the DC waveform, DC value, and obviously it will be DC value. It means that obviously we don't have pure DC after rectifier. We have, although we have the capacitors here, it means that something is smoothed out. More thing to add. So we have always the mean value and we have the voltage ripples. So what are those values? They are our major concerns. So let's discuss these things. So here you are having some the equations which are the standard equations for any practical Cockcroft-Walton circuit, and the first equation is the equation about voltage ripple. This equation gives us the value of how much there is the ripple in the voltage, and it is equal to load current divided by the frequency of this AC power source multiplied by the capacitance. So one more thing, in Cockcroft-Walton circuit, the values of capacitors throughout the circuit is the same value. Each capacitor will be having the same capacitance. So okay, and multiply by n into n plus 1 divided by 2. Now n is defined as the number of stages. So if you have a Cockcroft-Walton multiplier circuit, any circuit, so what will be the ripples in the output voltage? What is the value of the voltage ripple? You can calculate using this equation. Now how this equation is derived, we are not going to discuss that. This is none of our concern in this course. Yes, you can derive these equations as well, but we are not interested in that derivation because we are more interested in practical design and practical aspects. So what is IL? IL is actually the load current. Now we will be discussing about how much the voltage drop. There is another equation, an interesting equation, which is used to calculate the voltage drop. That is, it will be telling us that how much voltage will drop when you put in the test object, and that equation is equal to V drop is equal to, now this equation tells us actually delta V or delta V, yes, okay, delta V. When we will be covering the practical analysis, you will be more clear with this concept. Now this equation is equal to IL, which is the load current, divided by the frequency, the capacitance, into 2 by 3 n cube plus n square by 2 minus n by 6. Now this equation tells us the how much voltage will be dropped. I mean to say, let's say if V maximum is 100 kilovolt, and whatever the values of the capacitor, and your V drop or your delta V comes out to be 80 kilovolts, it means that there will be the drop of 20 kilovolts. Okay, there will be the drop of 20 kilovolts when you apply the test object having this load current and capacitors having these capacitance and the frequency whatever is the frequency. Again I repeat, let's say if here you have 100 kilovolts and sorry, if you, it is not actually mentioning in that way. We will be doing this concept when we will be analyzing the practical Cockcroft-Walton circuit, because at this time I don't think that this is more favorable to explain or get into that concept. At the moment, let's stick to this equation. Then here you can also see that delta V is directly proportional to IL, which is the loading current. Now we have another equation which helps us determining the optimum number of stages. What are the optimum number of stages for V max the given value? Let's say I say that I have 220 volts here, and what could be the optimum number of stages? Now 220 is what the RMS value. So what could, and the V max is actually what I told you, that V max is the peak value of the input waveform. So what could be the optimum number of stages? So here again we have an equation, NOP optimum is equal to under root V max multiplied by the frequency multiplied by the capacitance divided by IL. So this equation gives us the idea that what should be the optimum number of stages. Why the optimum number of stages? Such that your voltage drop and your voltage ripples are minimized. This value actually tells us that if you will be having this number of stages, then your voltage drop will be minimum as well as your voltage ripples will also be minimum. And now comes to another very important equation of this Cockcroft-Walton circuit, is that this equation tells us the maximum possible output value. Theoretically, what we say that this circuit, it does, it doubles the voltage, but practically you have voltage drop because you have the load current, you have the input frequency. So these factors define what will be the output voltage under the test object, and this is given by the equation V output maximum is equal to N optimum multiplied by 4 by 3 multiplied by V max. Now what is V max? V max is actually the input voltage here, the peak value of the input voltage. So this is the practical value. This equation gives us the information about the output voltage which you will achieve practically, and still we have ignored the diode voltage drops. They can be added, but they can be neglected. Whatever the voltage drop will be 1.4 volts if there are two diodes in series, or 1 volt, one diode will obviously drop about 0.7 to 1 volts. So this is the value of the output voltage. Now let's proceed to the analysis example of a Cockcroft-Walton multiplier circuit, and that example will clear most of your concerns about the practical design of this circuit. Okay, so in our next video lecture we are going to solve the practical numerical of this Cockcroft-Walton multiplier circuit, and we will also be looking at that how to choose these values of stages and the capacitors. So stay tuned for the next video. Thank you.